In this video, I will run a simple experiment to compare 5 different boosting ensemble models. These include XGBoost, LightGBM, CatBoost, Adaboost, and a vanilla gradient boosting classifier. I will first briefly mention what each of these models are before working through a comparison of these classifiers on a publicly available dataset. All coding shown in this video is done in a Jupyter notebook, and that notebook is available on my GitHub. You can find a link to this notebook in the description below. XGBoost is an implementation of the gradient boosting algorithm that is optimized for speed and performance and has become one of the most popular packages for applied machine learning problems. You can check out my previous video on XGBoost for more details. LightGBM is a newer implementation of gradient boost developed at Microsoft with a focus on performance and scalability. CatBoost is another newer implementation of gradient boost, but this time was developed by Yandex. Here the focus was to develop a model with the capability to handle categorical input predictive features. Adaboost is an older boosting model, originally developed in 1997, and the first boosting algorithm to gain wide popularity. You can check out my blog post on Adaboost classifiers for more details. You can find a link to this article in the description below. Now, I will also compare a vanilla gradient boosting classifier with all the other algorithms that I already mentioned. And originally, the gradient boosting algorithm was developed as a generalization to the aforementioned Adaboost algorithm. And now we can jump into a Jupyter notebook to compare how each of these different models compare on a particular problem. Okay, so now we're in our Jupyter notebook, and the first thing I'd like to mention is that this notebook is available on my GitHub. I have a link to this notebook in the description below, so you can download it and experiment with it as you see fit. So the first thing that I would like to do is import all the packages that will be required for this experiment. So let's just go ahead and run this cell and bring all those packages in. So the data set that we will be using here is the breast cancer data set that is available from the UC Irvine machine learning repository. I have a link to this data set in the description below. However, I've already downloaded these data, and so we can just read them into pandas just by running this cell. And now we can get a sense for the shape of the data. So this data set has a total of 10 columns, and we have 286 rows. So let's take a quick peek at some of the first few rows. And what jumps out immediately is that most of these columns actually contain strings rather than numerical values. So we'll have to treat for that somehow when training our models. Now, if we look at the website for this data set, it specifies that the class column is our target. And so this will have to be converted into a numerical value and separated from our predictor features, which are the remaining 9 columns. Now, when we take a peek at the values that we see here, we can see right away that the features age, menopause, tumor size, inv nodes, and degree malignancy are all ordeal. And what that means is that we have to preserve the sense of order in these columns. We can't just do something simple like one-hot encoding in order to convert these into numerical values. So that's something that we will have to treat for. Now on the flip side, the features node caps, breast, breast quad, and irradiate are all categorical, and so these can be dealt with through one-hot encoding. Now in addition, the website also states that missing values are present for node caps and breast quad. So let's investigate this a little bit further. Let's check out and see what the unique values of node caps are. And so here we see it's no, yes, and then this question mark. This question mark represents our missing values. So let's see how many missing values we've got. And there's a total of 8. Now let's do the same thing for breast quad, and we can see here again that the missing values are represented by this question mark. And there's a single sample in our data that has a missing value here. So now I'm just going to fill in these missing values in a very simplistic way, and that will be with the mode for each of these columns, or the most frequent entry for each of these columns. It's a very simple way, but it's suitable for the experiment that we're running here. Let's just run these cells. And now I will separate out the target from the predictor features. And so we can just create these two arrays, Y and X, which is more convenient for the rest of our analysis. And now I want to handle the ordeal columns that I mentioned previously. If we look at the website, we can see what the unique values for each of these ordeal columns should be and what their respective order is. So I've defined those in these lists. And now I can use these lists when declaring an instance of our ordeal encoder. Now this ordeal encoder is what was imported from scikit-learn. Let's set up our instance. And now with a single line, we can convert our ordeal columns into numerical values. And so that's what I'm going to run next. And now we see, if we look at our data again, we can see that our ordeal columns now have these nice integer values. So that's exactly what we want to see. Now the next step will be to convert the data types of our columns. And this is just useful for the modeling that we'll do later on. Basically, we'll complain if we have object types. So instead, I'm going to convert our categorical features into category types, and the rest will be integers. And finally, I want to convert the target we have from string values. So that's what we currently have. We have two unique values for our labels. It's no recurrence events and recurrence events. And I want to convert these into numerical values. So I'm going to set it to be 0 and 1. So 0 is for no recurrence events, 1 is for recurrence events. So the cell will take care of that. And now we see that our target just contains 0 and 1. So that's great. The last thing that I want to check is for class imbalance. So again, we have a total of 286 target labels. And of these, 201 have a label of 0, whereas 85 have a label of 1. So this is a clear case of class imbalance. So we want to deal with that before doing our comparison. So to that end, I've written this wrapper function, balanced train test split, and this is just a wrapper around the scikit-learn train test split function. And what we do here is we first do a train test split as normal, but then through sampling with replacement, I basically ensure that with the training data, we have an equal number of samples from both classes. So this just takes care of the class imbalance problem for training. The test set is unaffected. So now with all of that out of the way, we can proceed with our model comparison. The first thing that I want to highlight right away is that I'm not doing any hyperparameter tuning with this comparison. So I've just set the same set of hyperparameters for each of the models we're going to look at. Specifically, I've set the learning rate, the maximum depth, and the number of estimators for each ensemble. So now with XGBoost, let's do a train test split. And now I'm actually going to feed into XGBoost the data that includes the unprocessed categorical features. And this is a new feature of XGBoost as of version 1.5. We can do this by setting this boolean, enable categorical to true, and now XGBoost should be able to handle categorical features. So let's try that out, and let's time how long it takes to train the ensemble. So here we see that it took 0.3 seconds to train XGBoost, and there's no errors, so it appears to have worked, even though we haven't processed our categorical features. And so now let's evaluate how well our model did. And here you can see the results. The evaluation is done in terms of accuracy, precision, recall, and F1 score. So before we draw any conclusions based on these numbers, let's first run through the other models, and then we can use this as a point of comparison. So the next model we will look at is CatBoost. And like before, CatBoost can handle input categorical features. So we don't need to do any additional pre-processing for those columns. So let's just run CatBoost. And here we can see that the training time duration is 0.3 seconds like before. But the performance is worse. So compared to XGBoost, we're not doing as well for these data. Now let's move on to LightGBM. So in this case, we can't get around the fact that we have to include an additional pre-processing step for the categorical features. So the way I'm doing that is just through one-hot encoding. So I have to include this additional line here for the 4 categorical features. And then after that, I do my train test split. So let's go ahead and run this cell. And now I can train my LightGBM classifier. And here we can see it is a bit faster than the previous models at 0.28 seconds. So here we see the results from running the LightGBM, and we can see that the results are quite a bit better than what we saw previously, and that's across the board, across all the different metrics. Now let's move on to Adaboost, and like LightGBM, Adaboost requires the data where the categorical features are one-hot encoded. So we're reusing the same data as before. And here we can see that the training time is 0.29 seconds, but the results are better than before. In fact, these results are the best ones so far. You see the accuracy is 0.71, and we have an F1 score of 60. So this is pretty nice, actually. And now we'll go with our gradient boosting classifier. Like before, it requires the one-hot encoded features, and the training time is now the longest of all the models used. So this is 0.31 seconds, and the performance is also not that great in comparison. So I've already run this notebook before, and I've tabulated the results in this table here that we see below. Some of the computation times are a little bit different between runs. So here we can see that the GBM is the same as what we saw previously. With Adaboost, it's also the same at 0.29 seconds. However, LightGBM in this run took a little bit longer. It's 0.28 seconds as opposed to 0.27 for this previous run. However, the metrics are all equivalent across all different runs, so we don't have to worry about variations across accuracy, precision, recall, and F1 score. But if we look at this table, we can see right away that in terms of computation time, LightGBM is a little bit faster than the other models. However, in terms of performance, what seems to have worked best is Adaboost. Adaboost has the highest F1 score, it has the highest accuracy, the highest precision, and it's tied with LightGBM and XGBoost in terms of recall. So yeah, for these data at least, Adaboost is the clear winner, and it seems like the gradient boosting classifier and CatBoost are the ones that struggled the most with these data. Now it's important to keep in mind, and I want to stress 2 points here in terms of this comparison. One is that we didn't do any hyperparameter tuning, and so if we did include a separate hyperparameter tuning step for each of these models, these results could be different. The other thing to consider is that these results are contingent on the data we're using. So if we want to do a more thorough comparison of these models, we shouldn't use just one data set. We should in fact use many. We should use at least 5 or more, ideally as many as possible. But yeah, for the purpose of this video, I didn't want to make something that's an hour long. So this is just a very simple example of comparing these models and what it would take to do so. So this concludes this video on different boosting models. I hope you gained some value from this experiment and learned something new about different types of boosting models. If you enjoyed this content, please like the video and subscribe to the channel. It's always appreciated to receive this support. You can also subscribe to my newsletter, which is the best place to keep up to tabs with the different content that I produce, either on this YouTube channel or on my personal blog. So I have a link to sign up for my newsletter in the description below. So until next time, have a great day and see you in the next video.